The purpose for this lab is to observe the motion of a single object that is moving at a constant speed without changing direction and use a model to predict this observation. Doing so will allow us to have a good understanding of Newton's second law of motion and how to create models that accurately portray our observations. First, we will discuss our recorded observation and data collection process using Tracker. Next, we will apply the momentum theory to our system to predict the object's motion to create a model using GlowScript. Then, we will compare our model to our observation and discuss the similarities and differences between the two. Finally, we will answer some final discussion questions and conclude. So let's begin with our observation. Here, our system will be just the basketball, with surroundings as the ground, the air, and everything around it. The first frame starts a little after the ball has been pushed to give it time to stop accelerating and reach its constant velocity. The forces present will be my hand pushing the ball to the left, gravity pulling down on the ball, the floor pushing back up on the ball, floor friction, and air resistance. The origin is set at the center of the mass of the basketball. The ball will be moving left in the negative x direction. As the ball moves, the point masses are set to the center of the basketball. The length of the ball is calibrated for 0.75 meters. With these settings, we are able to collect our data regarding our position and velocity. Let's create our model now. Once again, our system is the ball. Here, we set our mass to 0.62 kilograms. We set our initial position to negative 0.002 meters, which we get from our tracker data. We compute our initial velocity by dividing the difference in the first two positions by the first track change in time to get negative 2.667 meters per second. We will use an iterative approach to predict the motion of our ball. We use Newton's second law to get our new velocity and then use the new velocity to predict the new position. We will do this every 0.01 seconds to predict the motion. We will stop at 1.333 seconds as that is when the tracker stopped tracking the ball. Let's run it. As you will see, it moves in the same direction as our observed basketball. Let's compare the two. Here, we can see the results of both the observed basketball and our model. Our initial velocity is negative 2.667 meters per second. Because we were experimenting with constant velocity, you will notice we are given straight lines. The line should be straight because if we are traveling at a constant velocity, our iterative process, which uses Newton's second law, will make sure our position moves the same distance each iteration. Recall, our net force is zero because we are experimenting with constant velocity, which will cancel out this part of the equation. Immediately, we can see a large difference in position for our experiment and our model towards the end. Our model's initial velocity overestimates where the ball is located at the end of our experiment. This tells us that our initial velocity was not exactly correct. There are multiple possible factors as to why this is. The basketball could have still been accelerating when we started tracking it and not yet at its constant velocity. Calibrating our center of mass could have been off, or our ball could have been rolling backwards some on the z-plane, which we did not take into consideration. We could improve our prediction model by calculating our initial velocity a different way. Using this equation, we take the difference of our initial position and final position and divide it by the total time of 1.333 seconds. As you see here, this model is more accurate. The slight discrepancies you see in the middle could be caused by the same reasons mentioned before, but this is an overall better model. Let's discuss some what-ifs. This graph is the result of if we flipped our axes. Our ball now moves along the x-axis in the positive direction instead of the negative like before. This in turn means both our velocity and position will be positive instead of negative. This question is important because it allows us to see that direction does play an important part in our results, as both position and velocity have a magnitude and a direction. With our net force being set to zero, our model does a fair job of predicting our observation. As far as forces that give us a net force of zero, we cannot determine the exact values of these forces, but we do have an idea of what forces are present. We know that my hand push is a force in the negative x direction. Friction from the ball rolling on the ground will push in the positive x direction, as well as air resistance. These together should give a force of zero. Gravity would be pushing down on the ball in the negative y direction, and the floor would be pushing back up on the ball in the positive y direction. These together should also give a total of zero force. All of these added together should give us a net force of zero. To conclude, with this lab, we tracked the motion of an object moving at a constant velocity and was able to predict this motion with the model. We noticed the differences in our predictions using two different initial velocities calculated different ways. We also made mention of what would happen if our axes were flipped. Finally, we considered which forces were acting on our system to give it a net force of zero. Thank you.